Welcome to ThirdEye Labs, where we make the unseen seen. Today we explore one of the most profound and widely used ideas in all of mathematics, the Fourier Transform. Whether you are compressing a photo, streaming music, scanning a body with an MRI, or training a neural network, this single algorithm is working quietly behind the scenes. Let us see how it works and why it is so powerful. Imagine you are handed a fruit smoothie and asked to figure out exactly how much apple, banana, and strawberry went into it. In the real world, unblending a smoothie is practically impossible, yet we face this exact problem constantly. A microphone records one messy waveform containing a singer, a guitar, and drums all at once. An EEG machine records the combined electrical chatter of millions of brain cells. We need a mathematical unblender. The story begins in 1822. The French mathematician Joseph Fourier was studying how heat flows through metal. He made a bold, controversial claim that any function could be built from a sum of simple sine waves. 50 years later, Lord Kelvin used Fourier's math to build a machine of brass gears and pulleys that predicted the ocean tides, separating the gravitational pulls of the sun and the moon. But the modern era ignited in 1965, when Cooley and Tukey published the fast Fourier Transform. This algorithmic shortcut made the calculation thousands of times faster, and it quietly became the engine of the entire digital world. JPEG, MP3, and MRI all rely on it. Before any calculus, picture a glass prism. White light enters as one messy beam, and the prism bends each color by a different amount, splitting it into a clean rainbow of pure frequencies. The Fourier transform is a mathematical prism. It takes a signal in the time domain and splits it into the frequency domain, revealing every pure frequency hidden inside. The transform's secret engine is Euler's formula, often called the most beautiful equation in mathematics. It says that e to the I theta equals cosine theta plus I sine theta. Geometrically, this is simply a point traveling around the unit circle. As the angle theta grows, the arrow spins. Its shadow on the horizontal axis traces a cosine wave, and its shadow on the vertical axis traces a sine wave. So this one term, e to the I theta, is a perfect, self-contained rotation. It is the spinning hand that the Fourier transform uses to probe a signal for every possible frequency. Fourier's controversial claim was that any repeating shape, even one with sharp corners, can be built by stacking simple sine waves. Let us try to build a square wave. With a single sine wave, the fit is rough. But watch as we add more harmonics. 3, then 7, then 15, then 51. The more harmonics we add, the closer we get to a perfect square. But notice the little overshoot that stubbornly clings to each sharp edge. It never fully disappears. This is the famous Gibbs phenomenon, and it is why sharp edges are the hardest thing to compress. Here is the most beautiful consequence of Fourier's idea. Each frequency component is really a rotating circle, an epicycle. Stack enough of them, tip to tail, each spinning at its own speed, and their combined tip can trace out absolutely any shape. Watch the 40 spinning circles on the left. The biggest circles capture the broad strokes, the tiny fast ones add the fine detail. As they turn, the glowing pen at the very end draws the target curve, one frequency at a time. This is the Fourier transform, made visible. Now the formal equation. Do not let the calculus intimidate you. Every single piece has a clear, physical meaning that we have already seen. On the left, capital X of f is our output, the strength and phase of one specific frequency hidden in the signal. On the right, little x of t is our input, the messy signal measured over time. This rotating term, e to the minus I, 2 pi, ft, is the winding machine from Euler's formula. It wraps the signal around a circle at frequency f. And the integral sums it all up, computing the center of mass of that wound-up signal. When a frequency is present, the mass bulges to one side. If not, it cancels to 0. Let us plug in real numbers. Our input is a pure 2 Hz cosine wave, 2 beats every second. On the right is the complex plane, our winding machine. We wind the signal around the circle at some test speed. At half a hertz, the wound-up shape is lopsided, but its center of mass, the red dot, stays near the origin. Now watch as the winding speed climbs toward 2 Hz, matching the signal itself. Every peak of the wave suddenly lines up on one side of the circle. Look at the center of mass. It lurches far out from the origin. The integral has caught the signal. The distance of this red dot from the center is precisely the value of the Fourier transform at 2 Hz. It is the math shouting, yes, there is a 2 Hz tone in here. Push past it to 3 Hz and the peaks fall out of step again. The center of mass collapses back to 0. The transform reports, no 3 Hz tone here. Let us see this in 3 dimensions. Time flows along the horizontal axis, while the complex plane, our winding machine, stands perpendicular to it. As time pushes forward, the rotation twists the signal into a 3-dimensional corkscrew. Taking the Fourier transform is like staring straight down the time axis, flattening this spiral, and asking a single question. Is the coil off-center? The clean integral assumes infinite continuous data, but a computer only has a finite list of samples. So in practice, we use the discrete Fourier transform, the DFT. It replaces the integral with a sum over n samples. Same idea, probe each frequency by multiplying with a spinning exponential, then add it all up. But there is a catch. Computing the DFT directly costs n² operations. For million samples, that is a trillion multiplications. The breakthrough of Cooley and Tukey was the fast Fourier transform, which cleverly reuses repeated calculations to cut the cost to n log n. For that same million samples, it is the difference between a trillion operations and about 20 million, thousands of times faster. This single speedup is what made digital signal processing practical. Here is the most dangerous practical trap. When we sample a signal, we only capture snapshots at fixed moments. Here is a true 8 Hz wave. Now suppose we sample it too slowly, only 5 times a second. Look only at the sampled dots and connect them. A completely false low frequency appears out of nowhere. The fast wave is masquerading as a slow one. This is aliasing, the same effect that makes car wheels appear to spin backward on film. The Nyquist theorem gives the cure. To capture a frequency safely, you must sample at more than twice that frequency. It is why CD audio uses 44,000 samples per second to capture sound up to 20,000 Hz. Here is the property that turns the Fourier transform from elegant into indispensable: the convolution theorem. Convolution, the operation behind blurring an image, filtering audio, and every layer of a convolutional neural network, is slow and expensive in the time domain. But the theorem says, convolving 2 signals in time is exactly the same as simply multiplying their Fourier transforms in the frequency domain. So instead of a costly sliding and summing operation, you transform, multiply point by point, and transform back. This is how large filters run in real time, and it is a cornerstone of fast, modern machine learning. Let us watch it solve a real problem. You record a podcast, but a refrigerator hums in the background, a high-pitched whine mixed into your voice. Run it through an FFT, and the messy squiggle becomes a clean spectrum of frequencies. Your voice is the strong low peak. The annoying hum is an isolated spike way up high. Because the transform is perfectly reversible, you simply delete that spike and run the inverse transform back to time. The hum is mathematically erased, leaving crystal clear audio. And the very same logic powers JPEG image compression and MRI medical imaging. In an MRI scanner, the raw measurements are literally Fourier coefficients. The image you see is reconstructed by an inverse transform. The plane transform tells you which frequencies exist, but not when. For music or speech, that is not enough. The solution is the spectrogram, built from the short-time Fourier transform. We slide a small window across the signal and take a transform at each step. The result is a heat map. Time runs left to right, frequency bottom to top, and brightness shows how much of each frequency is present at that moment. Here you can clearly see a tone that rises over time, a chirp, along with its harmonic above it. And here is a real spectrogram of actual recorded sound. This is exactly how a music visualizer, or a speech recognition front-end, sees the world, not as a wave, but as a living picture of frequency over time. A final caution: the transform does not give unlimited information. It obeys a fundamental trade-off, mathematically identical to Heisenberg's uncertainty principle in quantum physics. A sound that lasts a long time, like a sustained piano note, is spread out in time but razor-sharp in frequency. We know its pitch exactly, but a sound that happens in an instant, like a sharp clap, is pinpointed in time yet smeared across all frequencies. You cannot know exactly when an event happened and exactly what frequency it was at the same time. The Fourier transform is the gateway to a whole family of tools. If your signals decay over time, study the Laplace transform. If you need both time and frequency precision, explore wavelets, which beat the uncertainty trade-off by analyzing multiple scales at once. And in modern machine learning, Fourier ideas are everywhere. Fourier features and positional encodings let transformers represent position and high-frequency detail. And Fourier neural operators learn to solve physics equations directly in frequency space, blending 2 centuries of mathematics with deep learning. To recap, the Fourier transform is a mathematical unblender. Using Euler's spinning exponential, it winds a signal around a circle and measures the center of mass to reveal the frequencies hidden inside. The fast Fourier transform makes it lightning quick, and the convolution theorem makes it the secret engine of filtering and machine learning. Master this one idea, and you gain an entirely new lens for understanding data, sound, light, and the universe itself. Thank you for watching, and keep exploring. Please like and subscribe ThirdEye Labs if you enjoyed this video, and let me know in the comments.